Question 1 here says, let S be the region enclosed between the graph of f of x equals the square root of x, the x-axis, and the vertical line x equals 4. And part A says to compute the area of the region S. So the first thing we're going to do is we're going to graph the square root of x here. This is a relatively simple graph. You can just go through like the square root of 0 is 0, the square root of 1 is equal to 1. We'll go up to 4 here because the square root of 4 is 2, and then connect them like this. You don't have to be perfect when you're doing these problems, although the more accurate you are, usually the better it'll be. Okay, so that's the graph of the square root of x here. Now let's graph the vertical line x equals 4. This will be really easy, just a vertical line right here. So the region S that we're worried about here is going to be this region right here. Right? This is the region bound by the square root of x. The x-axis starts over here at 0 and ends at x equals 4. So how do you find the area of a region S? Well, to find the area under a curve, you're going to integrate. So we're going to integrate the square root of x, our function, of course. We're going to do that with respect to x. Then our limits of integration are going to go from 0 to 4. So let's go ahead and compute this. First of all, let's change this so it's to the power of 1/2. Then let's add 1 to the exponent and divide by that new number. Now when you're doing problems like these, usually it's better, instead of dividing by a fraction, like instead of dividing by 3/2, it's better to multiply by 2/3 because it's just a little bit easier to do the math that's about to happen. So what we're about to do is we're going to plug 4 in, and then we're going to plug 0 in and find the difference between the two. Now if I plug 0 in here, I'm just going to get 0. So I can actually ignore this piece here. So what I'm going to do is I'm going to plug 4 in for x. But I'm actually not going to just straight up plug 4 in, because I noticed something here. Right, we're raising it to a fractional exponent, which is a little strange. But 4 is actually just 2 squared, right? So I can rewrite this as 2 squared here. And the reason why this is helpful is because when you have this set up here with a fraction, or excuse me, when you have an exponent raised to another exponent with parentheses like this, you multiply the exponents together. So you're going to get 2 times 3/2. That means this 2 will cancel with that 2. You'll just be left with 2 to the power of 3 here. 2 to the power of 3, of course, is 8. And then finally, we get to do 8 times 2/3, which gives us 16/3. And that's the answer. That is the area of this region right here. Part B says find the value of c such that the vertical line x equals c divides the area into 2 equal parts of equal area. So if we come over here to the graph and we start at 0 and go to 4, there's going to be some point where if we divide this up like this, actually here, I'm going to try to eyeball it first. There's going to be some point where when we cut this at a certain specific location, the area of one side will be equal to the area of the other side. So here's how we're going to approach this problem. We are going to do the integral, just like we were doing. It'll be of the square root of x. But instead of going from 0 to 4 like we did last time, we're going to go from 0 to this unknown value here, c. So if the entire region was 16/3 and we're trying to split this up into 2 halves, that means we're going to take half of 16/3. So that's exactly what I'm going to write over here. I'm going to do 1/2 of 16/3 like this. All right, so let's go ahead and let's actually do the math here and see what happens. We already computed the integral of the square root of x. Remember, it turned into 2/3 x to the 3/2. But instead of going from 0 to 4, it's 0 to c. Over here, half of 16/3 will give us 8/3 like this. Also, just like before, when we plug 0 in for x, we're just going to get 0. So what we're going to do is we're going to plug in the top limit here, which is c. There we go. Okay, this is looking pretty good. Let's multiply both sides by, let's see here, it should be 3/2 is what we're going to multiply both sides by. So over here, well, this is nice because the 3's will cancel. That will cancel with that, leaving us with a 4 there. Now we have c to the 3 halves equals 4. And now we're going to raise both sides to the 2/3 power. Now there's a couple different ways that we could write out our final answer. One way is we could just leave it like this, 4 to the 2/3. We could also leave this as the cubed root of 4 squared. 4 squared is also 16, so you could do the cubed root of 16 as well. Another thing you could do is that 16 is actually just 8 times 2. The cubed root of 8 is equal to 2, so you could say it's equal to 2 cubed root of 2. Now, if you really want, you can take this and plug it into a calculator. So let me do that really quickly. Let's figure out what the cubed root of, I'll just do the cubed root of 16. I think that'll be the easiest to plug into the calculator. And we get 2.5198. So actually, over here, when I was just sort of estimating where this line could go, I wasn't too far off. It should be a little bit closer to 2.5. But that is the answer. Part C here says, imagine rotating the region S around the x-axis to create a solid of revolution. Find the volume of this solid. So anytime you're doing a solid of revolution question, you're either going to use the disk method, the washer method, or the shell method. In this case, we're going to be using the disk method. And the formula for the disk method looks like this. Pi integral r squared dx from a to b. And really what you have to do is figure out what r is equal to. Then you can just plug everything into the formula. So like down here, I'm just kind of creating a blank space for us. Once we figure out what r is, we'll plug it in here. You also have to figure out a and b. Let's actually start there because that's the easiest spot. A and b is the limits of integration, essentially, that we've been using. It's going to be 0 and 4 here, right? We start here. There's our a value. We end over here. That's our b value at 4. Okay, but what is r and how do we find it? Well, here's what we do. You notice that it said that we're going to rotate around the x-axis. So let's come over here. Let's draw a little arrow indicating that we are rotating this about the x-axis like this. Then what we're going to do is we're going to draw in a rectangle. And this rectangle has to be perpendicular to the axis of rotation, like this. And it has to touch the function up here, like this. It has to be bound between the lower part, the axis of revolution, and the upper part. We're going to call the width of our triangle delta x. And here we go. This is it right here. R is the distance from the axis of rotation here up to the top of this curve here. You could think of it kind of like the height of this rectangle I drew in here. Now, I just drew this rectangle here in the middle, but I could have drawn it anywhere, and depending on where you draw it, this rectangle will be taller or shorter. So we need an equation that will give us the height of this rectangle, no matter where you decide to draw it. And that's going to be based off of our top function here, right? Because we draw it from down here, and then we stop once we hit our top function. So really, r is equal to the square root of x. Now that I know what r is, I can come down here and plug it in. Square root of x. The square root of x squared is simply x, and now we can continue from here. So we're going to get the pi in front. We're going to get x squared over 2. We're going to go from 0 to 4. If we plug 0 in, we're just going to get 0, so I'm not going to worry about that. But I am going to plug 4 in. 4 squared is 16. 16 divided by 2 is 8. So our final answer is going to be 8 pi. Part D here says find the x value, d, such that rotating the two subregions split at x equals d around the x-axis gives two solids with equal volume. So if you look over here, we have the same drawing we had from before. What we're going to do is we're going to call this rectangle area here D. And we don't know where this is yet, but somewhere along here, if we pick this spot, we're going to get two equal volumes here if we create a solid of revolution. So we're going to use the same integral that we had from before, where we have pi times r squared, and r, we discovered, was the square root of x. But instead of going from 0 to 4, we're going to go from 0 to d like this. And then because we want two equal volumes, well, remember, we found the volume was 8 pi. All we have to do is divide that by 2. So, okay, let's start by evaluating this integral over here. The square root of x squared is just x. Once you find the integral, you're just going to get x squared over 2 from 0 to d. 8 divided by 2 is 4. When we plug 0 in, we're just going to get 0, so I'm not going to worry about that. When we plug d in, we're going to get d squared here. Now what we're going to do is we're going to multiply both sides by 2 over pi. That way these pi's are gone, these 2's are gone. Nicely over here, those 2 pi's will be gone. So we got d squared is equal to 8, which means that d is equal to plus or minus the square root of 8. But of course, we don't want the negative square root of 8. We want the positive square root of 8 for this particular problem. And if you plug that into a calculator, that gives us around 2.828. So somewhere actually closer to 3, somewhere over here, is where we would have to draw the line to get 2 equal volumes.
If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.